This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Yo.
Okay. Right. Okay, so we're going to quickly finish off the last lecture. And then we'll move on to continuous dynamics, because it's going to set us up for automata, which is what we're going to be doing over the next few weeks, okay? So before I start, I've had multiple questions about the assignment. In particular, the caching problem. Okay, so there is a book, a very good book, called That, if you can read it. What's that? Oh, yeah, that's my bookmark, yeah. Yeah, go MUR. Anyway, in this book, it has something like, hey, you can even see my old student number. Hey. Anyway, you can see there is 103 pages on memory hierarchy design. In particular, it's the basics of caches, cache missing, set associativity, all of that sort of stuff in there. It's a great reference. Okay, so what I can do for you is, look, it even gives you examples. It's very hard to see on this, but it gives you examples about the different types of associativity, right? In terms of set associativity, direct map, or fully associative, right? So what I can do for you is I can, if you can come across this book, good on you. But if not, I can photocopy just a bit of this section here about caching to give you some more in-depth detail about how the offsets and the tags and stuff work. Okay, so if you're happy with that, I'll put that up. It's got a very good example here about how the tags and the indexes or sets work. Mind you, it's a bit old. I realise it's still got the price tag on there, and if you really zoom in, you can even see the date when I bought it. I was actually in third year. This was our third year textbook. So for one of the 14 subjects that I did in third year. So it's a very good book, and so I think it's up to the 6th edition. So I will photocopy some of that stuff and put it on up there on LMS for you. And it cost $75 back in 1999. Okay, so right, we are going to just briefly finish talking about I/O in terms of interrupts, because I want it to raise some important questions that will get touched upon over the next 2 to 3 weeks when we start looking at state machines and timed automata. Okay, so what happened way back when? This is a little bit of code from an AVR type embedded system, and you notice it's got this magic I/O header here that's specific to the architecture, and there were these magic lines here that set up a timer which was going to generate interrupts for us at a particular rate, right? Say every 1 millisecond. Now this, if you would have noticed, it doesn't look like C code. It just looks like you're assigning values to, I don't know, constants or something. Well, it couldn't be constants. Well, maybe they're constants. Who knows? But that's not the case. If you go on a bit of a rabbit hunt, no, don't call it a rabbit hunt, going down a rabbit hole, and you start pulling out the headers and you start looking at what's in there, you find that that TCCR 1A is defined as something, which is defined as something else, which is defined as something else. And eventually you pull out the fact that all of that is actually, that's what it corresponds to. What the heck is going on here? You are dereferencing some pointer, and the memory location it's pointing to is OX80. What this really does is, this whole line here just writes the value, what is it, OX00, into memory location OX80, hexadecimal, right? Remember, we're down at the bare bones, you know, getting down to the bare bones sort of bare metal of this thing here. So we are writing a value to a register location. That's actually a memory mapped register in this architecture. And the next line also, it writes a different value. It writes hexadecimal 0C to, if you go and chase up in the headers, where it's defined OX81. Now, the idea behind all of this is that this is architecture dependent. You're actually writing a value into a timer, right? The value C. The top end of the timer is 0 and the bottom end of the timer is C. And the timer takes up 2 register locations. But the point is that using nice bits of code here where someone has already gone and defined these for you means that you don't need to be worrying about what these real locations are. Okay, someone pre-packages them in a header file for you with sort of English names so you know what they are. Okay, so that's what that's doing. You are dereferencing, can just point to it, dereferencing memory location OX80, and you're writing into it 0. So you're actually writing into a register. It's a memory map register. Okay, so this is what you'll see if you do something on maybe another type of architecture, like an ARM architecture or something. You'll get similar sorts of things. Nice, defined, capital, looks like registers, but they're not. They actually do the write. They're actually doing the write into it. Okay, so I don't want to go on too much about this because it's just a very small example, and this slide was missing from the original set I put up. I forgot where I needed to define some stuff. Things are done for you. That's the moral of this slide here. That this is a piece of code from ARM Cortex M3. And you are basically given a whole bunch of built-in functions as part of the IDE or stuff you get provided with when you buy a chip like this in order to do interrupts. So there are functions that allow a little system timer to be enabled, and also you can run this function in order to make it generate an interrupt. So in C, a lot of that's hidden from you, right? You get given these nice functions to be able to turn things on and off, turn the interrupts on, turn the interrupts off, enable, disable. So that's all I need to say there. So that means if you're writing an interrupt for this M3 ARM chip here, it's as simple as using their built-in functions and then writing your own interrupt service routine and your own code. So what does all this do here? We're going to generate, the whole goal is let's do something for 2 seconds. So we're going to set up a timer for a certain value, let it tick down, and then after 2 seconds, hopefully, you know, it causes an interrupt or do something, right? So here, let's look at the main function here. This line here, that's a built-in function as part of the ARM instruction, or not instruction set, code that you get, which registers this function, ISR. That's the address of that function, because the function will live at a memory location, right? It's a bunch of instructions in memory. And it says, okay, register some code living at that location to be invoked on every systic interrupt, which is 1 millisecond. So you can set it all up here to set it up to be equal to 1 millisecond. You get the system clock, you divide by 1,000. And here, you basically register this function will run every time an interrupt is generated, every 1 millisecond. And then how do you actually use that? Well, what happens is you set some good old C variable to be equal to a timer, and then you just let things happen down here, right? A piece of code while the timer is not equal to 0. Now, what's happening? This piece of code is actually, these two pieces of code are being run concurrently. So while this piece of code in here is doing something, every time, every 1 millisecond, the timer is generating an interrupt, it's branching to this, it's decrementing a variable, a volatile variable, I'll explain that in a minute, decrementing the variable outside of this function, right? It's playing around with it in the background. But you are checking it here in order to check when it hits 0. Okay, so that's the idea. You've got a little interrupt that's ticking this down in the background, and then once this hits 0, this loop breaks. So you would assume that your code would run for 2 seconds here. Now, how you do this is you define that variable as a volatile variable defined outside of the function, so it's viewable by all the functions, but you declare it as volatile. Now, if you haven't seen volatile before, it tells the compiler that the variable may change at any time. In other words, it tells the compiler, don't ever optimize this guy out. Okay? When you GCC some stuff, you can accidentally optimize things because it thinks it knows better and removes it. And it also basically tells the compiler not to cache it, okay? Because it tells it to put it in a register as opposed to make it live in main memory or caching it, okay? Because that's just the way that this works. You want it in a register, it's going to be accessed all the time, etc. Okay, so this is concurrent code. It runs logically at the same time. There's a hardware process that's always calling this whenever a 1 millisecond tick has happened on the clock and decrementing your timer count. So what could go wrong with this particular piece of code? When we have interrupts and concurrency, a classic case would be what happens if inside this loop here, and this is some code you might, I don't know, you might have print some stuff or whatever, there might be a lot of coding here, but if the interrupt happens twice inside this code, or maybe more than that, maybe 5 times, right? It's decrementing the timer count. By the time you get back to the bottom of the while loop, timer count may actually be less than 0. It might have crept below 0. And what that means is obviously you haven't run for 2 seconds. You've probably run something for more than 2 seconds, especially well, if timer count's less than 0. So there's a problem. All right, well, what can we do? Well, let's just do a bit of modification. Let's modify here inside this little interrupt routine that's called every time the timer generates an interrupt. And let's just check if it's equal to 0 in there. And if it's not equal to 0, we decrement it. If it is, we don't do anything to it. Okay, that might seem a little better, but we still have a problem. What happens if an interrupt occurs right here? Well, if we allow nested interrupts, then it can call itself and call itself and call itself, and that check may never work as we expected it to. In particular, if this ISR code was actually quite long, right, lots of instructions in here, then multiple timing events can happen, and it could potentially, if you allow nested interrupts, call itself many times. It might start getting really, really messy. So what we typically do is, when an interrupt's called, so a piece of code's running, interrupt happens, jumps up here, we disable interrupts from happening. Okay, because we don't want interrupts to happen while we're still decrementing a counter, or even before we've got to decrementing the counter and another interrupt comes in. Okay, so what we do is we disable interrupts. So, and this sometimes is actually built into the hardware. Sometimes the hardware itself disables an interrupt as soon as one occurs. It automatically does it for you, right? Because it's a hardware thing. You've got to catch it straight away. Software's too slow to catch things. Okay, so you disable interrupts, allow it to process it, and when you finish the service routine, you then enable them again. Okay, so you can see just from this example. Yeah, question?
Why can't you just use greater than 0?
Greater than 0 here.
Nah, the bottom one.
While it's greater than 0? Yeah, well, it's still the same problem. When is this comparison being made? Let's pretend there's, just to make it simple, let's pretend there's 500 lines of code inside that while loop, right? The comparison is only made when you hit the bottom of the while loop. You then check it again. Okay, so in C, ordinary C, that might be all right, but somewhere in here, this guy's been decremented over and over and over and over and over, and you don't check it till you hit the bottom when you get back to here to check your while condition. Okay, so it doesn't matter if that's not equals or greater than. The problem is if there's lots of code in here, you may overrun it. Okay? It's a good question though. So this is the problem with interrupts. They're fantastic because they respond straight away to things, events. But, wow, look at all the can of worms it opens up. The ISR execution time should be as short as possible. In this case, it's pretty simple. It just actually decreases a variable and does a comparison as well. Very short, only a few instructions. Because every time the ISR is called, it's chewing up valuable time. How long does it take to switch context? Remember, these things don't run in parallel. They run concurrently. They don't run on independent hardware units. They run concurrently. So switching between here, when an interrupt comes to here, may take time. In fact, it takes quite a few cycles. Pushing the program counter onto a stack, pushing the registers onto the stack to remember what they were, and then branching to the interrupt service routine, doing what you've got to do, pulling everything back off the stack again. 1 millisecond later, it all happens again. Push the program counter onto the stack, push the registers onto the stack, etc., right? So the context switch time is important as well. If you allow nested interrupts, so you allow one interrupt to happen, and while you're servicing that, another one comes and you start servicing that, and then another one comes, that starts getting complicated. You need some sort of priority system for allowing that to happen. Can ISRs interact with things that are happening in the main application? So back here, can I do things in here that can affect what's going on in here? Is that allowed? It makes the predictability of the code very difficult to do, right? Because if this can change things in here, then, wow, then you run this twice, it may never do the same thing twice. And lastly, more complicated, can interrupt service routines interact between each other? So can they do things like changing variables and stuff between each other? Wow, so if you have multiple interrupts firing, they could be messing things up like crazy, okay? So this is a little example just to show you how fraught interrupts can be, particularly when we want to run little software timers like this. It's a software timer based on a hardware interrupt. Okay, so we have to be really careful about this stuff. If you ever deal with interrupts, you'll never want to deal with them again, particularly with timers, okay? Because it's critical, the architecture. So this is the problem. Interrupts introduce non-determinism in computation, and that's kind of bad. As computer scientists or as programmers, you're always taught that a computer program is deterministic. You run it once, out comes some output. You run it again, same output. For the same parameters, you get the same output every time. But with interrupts, that just messes everything up, okay? You'll get different operation at different times. So don't be blasé if you ever use interrupts with embedded processors, but be very careful about how you use them and understand the consequences of their use. Okay, so we could go on forever about interrupts. I'd like to move on to our next lecture, which is on continuous dynamics, which I understand. Well, firstly, we'll talk a little bit about determinism, so it follows nicely from what happens with interrupts. But there's a bit of control-y stuff in here. So if you who's done control systems, by the way? Can I have a... Okay, about half of you. A knowledge of control systems is not important. Okay, we're going to talk about what's called actor models of systems, which essentially means things like Simulink and things like that, the software side of stuff. Okay? So let's have a look. So let's talk about models. And this is going to be the focus of what we're going to be doing over the next few weeks. We are going to be modelling things that you've never modelled before. Okay? Whoops. Oh, no, that's right. Right, so science. In science, we ramble on about how good a model is in how closely it matches a physical system. Okay, if it's close, it's good. If it's not, it's bad. In engineering, and sometimes it's very hard to get out of the scientific mindset, the value of the physical system has value, lies in how well its behaviour matches that of the model. That almost doesn't make sense, but think about it. Science is generally looking at the forces of nature and that sort of stuff. Engineering, we are looking at things that we've actually built. Okay, these are constructed things, right? So the value of the physical system lies in how well its behaviour matches that of the model. And in engineering, model fidelity, so the accuracy of a model, it's a two-way street. Or you can think of it this way. For a model to be useful, it's necessary for to be able, well, I put it twice, to be able to construct a faithful physical realisation. Okay, so for a model to be useful, we actually have to be able to make a faithful representation of the model. It's almost like a bent, warped opposite of what science does. I'll give you an example. There's a model. Okay, it's a Newton cradle, and the animation stopped. But anyway, you get the idea. It runs forever because they're elastic collisions, yada, yada, yada. And if you do that for a cheap, dodgy one you buy on the internet, what happens? Well, eventually, it's doing all right, but eventually it doesn't last long, right? It was cheap, come on. It's actually really underwhelming to have to keep pulling that ball and letting it go every time. So, oh, there you go, you get to watch it again. Right, so model, physical realisation. Now to a scientist, scientists would tell me the model is flawed. The model is flawed, right? There must be friction and all sorts of stuff in there. To engineers, the realisation is what's flawed. And I'm an engineer, not a scientist. Okay, and you are too, Master Engineering. So it's the realisation that's the problem. Why is the realisation the problem? Because the question is not whether deterministic models, so ones we can predict, describe the behaviour of these cyber-physical systems, okay? The question is whether we can build the systems whose behaviour matches that of a deterministic model. Okay? That's our focus as engineers, to build stuff. So if we have a deterministic model and we can make something based on that deterministic model, hey, that's great because it means it's deterministic. We can predict its behaviour, right? It's very different to science, looking at nature and trying to make some model out of it, right? Okay, but deterministic models, right? If you think, oh, it's deterministic, that's easy. Well, I know exactly what's going to happen and all that sort of stuff. But it still means you don't need to make it robust or fault tolerant, vulnerable to faults. It's actually the converse. Deterministic models enable designs because they make it much clearer what it means to have a fault. Okay, because it's deterministic. It's not some random stuff that happens and you've got no idea where it's happened or even maybe what's happened. Okay? So I want you to be thinking when we move over the next few weeks and we look at state machines and stuff like that and hybrid systems, this is the problem. We've got to change the question. Okay? Can we build cyber-physical systems, embedded systems that interact with the computer in the real world whose behaviour matches that of a deterministic model? Because if we can, we're perfect because we know there's a direct mapping between the two. Okay, so models. Models are abstractions of system dynamics, stuff changing over time. So in particular, I'm sure we've done a hell of a lot of that. If you've done control systems, and even the one under it, if you've done mechanics, if you've done any physics, really, even chem and maybe dispersion and stuff like that, you're modelling physical phenomena via ODEs, or just differential equations. When you're doing feedback control, you're modelling time domain signals, or, well, systems, or you could be doing discrete time. We are going to focus in modelling modal behaviour. And this lecture, well, I'll skim over the control stuff. I want to motivate it by talking about what modal behaviour is. So you're talking about FSMs and hybrid automata. These are systems where you've got continuous dynamics on one side and you've got a sequential system, computer system basically on the other. Okay, that's a hybrid system. Modelling sensors, hardware and software, so issues with concurrency and networks and all that sort of stuff. Okay, so our focus will be, we'll look at modelling the physical phenomena and a new way of doing it, and that's going to lead into something that's completely new to you, modelling modal behaviour over the next couple of weeks. Okay, so as I said, I'm not going to go on about it too much. Engineering mechanics up the top, or mechanical dynamics, or I don't know, one of those subjects that you might have done if you're a mechatronics student. If you're an electrical student, you've got PID controllers here, right? Yay. And under here it looks like a pole placement algorithm, something like that, right? So ODEs, Laplace transforms, feedback control models, all that sort of stuff. Modelling some real-world system because we live on the T domain where it's all smooth, right? We don't operate in discrete chunks of time. So the example I'm going to give you is a really dumbed-down version of a helicopter, and I'm going to frame it in a very different way that underscores our look at hybrid systems, okay? Fundamental parts of a helicopter. I'm sure you know the fundamental parts of the helicopter. But it's a difficult problem. It's unlike a car in that you've got, well, okay, if you don't take, you assume that suspension travel and stuff in a car is not too bad. But in a helicopter, you've got 6 degrees of freedom. You've got your X, Y, and Z lateral movements, and then you've got the orientation of the actual machine itself. And as you would have seen from using the Y-motes, you've got pitch, yaw, and roll, okay, about the various axes, X, Y, and Z. Okay, so when you are modelling continuous dynamics, you have to be very, very formal about how you model them. And that means introducing mapping notation. And we're going to do that for hybrid systems and timed automata and that sort of stuff when we get to it. So this is pretty simple. Position is given by 3 functions, and these are mappings from real numbers to real numbers. What are they mapping? A time point, so that's your domain, and your codomain, or the range here, is the position on an axis, okay? Sometimes we can restrict time to, say, r+, which is just t greater than 0. If we choose a chopping time to say, let's say time starts now. Okay, so we could group everything together into a vector, and it's a vector that maps from time into the 3 positional functions, x, y, z. What else is important? Velocity, well, that's just the derivative of this big x vector here, and it's the time derivative. And vector differential equations, right, derivatives work on vectors, right, component-wise, so it's no problems. And we can take the second derivative to get acceleration. Force, again, is a function that maps from time into the 3 dimensions because the force can act in all 3 axes or projections onto those axes. Okay, so Newton's second law says F equals ma. But we're in 3D now, so we've got to be careful, and so the force is a vector and the acceleration x double dot is also a vector. Now, when we are solving these things, we never use this really, because we are usually interested in the position of something. Okay, and this is like the dead reckoning idea. So if we want to work out what the position is here, we have a double derivative. We need to do double integration. So we need to integrate this twice. So we can convert our little equation here in terms of an integral equation to give us a position of x at any time t, noting that x is in R3, okay? It's across 3 dimensions. And we've got dummy variables galore going on in here. Now remember that when you do solve integral equations, right, every time you integrate something, you've got an initial condition. So we've got double integration, we've got an initial position and an initial velocity, okay, because we've got 2 integrations happening here. Oh, okay, we still haven't set up the problem yet. So what we want is, because that's just in the 3 dimensions, but we're going to particularly look at the orientation of the helicopter. And there are 3 things which we can think about in terms of the orientation. The angle with respect to each of the 3 axes, okay, so how you're aligned within our axis setup. Then the derivative of that, which is the angular velocity, and the double derivative, which is the angular acceleration. Okay? Lastly, torque, oh, I've just realised there's a typo here. Lastly, torque is, we'll see what torque is, but torque maps in 3 dimensions as well. And it's the force about rotating something. Now, I've got, this looks like a mistake here, so can I white these out? So these shouldn't be dotted, right? Obviously. So the orientation can be separated into 3 components. They're so important, the X, Y, and Z, we give them English names. So roll is about the X-axis, yaw is about the Y, and pitch is about the Z, right, up and down. So I can't, on this computer, I can't delete those things. So please delete those dots. They shouldn't be the derivatives. Okay, finally, let's do some modelling. Right. So a helicopter, well, what we're going to see is it wants to rotate. Now, once again, I don't care so much about the physics here, but there's a nice little animation. It shows you the angular momentum colour-coded. The momentum is this object swings around, a point mass rotating about a fixed axis, and the torque that it generates in the y direction in yellow, right? So torque is a twist. So force is like a lateral push, and you apply a torque, you do a twist. I hate the word moment, right? I'm a physicist. Well, I have a physics degree as well, so I always say torque rather than moment. Moment's like a mech-eng thing. I don't know why they love doing that. All right, so finally, the rotational version of Newton's second law, right? Because the helicopter's going to be governed by rotation. And it starts getting fun. You start talking about tensors and stuff like that, right? So I'm pretty sure you probably haven't, I don't know, has anyone done tensors before? Yeah, good, yeah. I first did them in physics, funnily enough, so when you're doing general relativity and all that. So blah, 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 blah. Basically, the torques in the 3 dimensions are this big differential matrix style equation. So these are the angular velocities about the axes. You differentiate them, but you've got all these coefficients, if you like, or functions in here that are in the tensor. I don't care too much about all that stuff. The point is that the helicopter, this one here, looks cool because it's got a V-tail on it, but it will never work because the rotor's spinning in order to give it, allow it to go up and down and forwards and backwards by tilting it slightly. With the friction in the shaft here, basically, it will just start spinning around by itself. If you've ever seen a helicopter with the rear rotor fail, you get a fun ride for not long and then it goes down. So it goes round and round and round. All right, so that's the yaw. So we're going to consider ourselves, let's keep it really simple. Let's forget about all the F equals ma stuff, so the lateral accelerations in the dimensions. Let's just look at torque. That's the yaw. We're going to look at the yaw, so the rotation about the y-axis. And everything in that previous equation back here, if we neglect about any other axes, the tensor and everything just collapses. The double derivative is just one component. We've got a coefficient here of moment of inertia, and we've got the torque. So this looks exactly like our good old F equals ma from before, but it's a rotational version. And we want to integrate this. Okay, the concept is, right, if you want a helicopter with a main rotor going, you want it to be stationary, not yawing. Okay, in other words, you may want it aligned such that theta y might be 0, for instance. Okay, so it's not angled with respect to the y-axis. So we can integrate this, good. And we obviously, if we integrate once, we need an initial condition. Now, that's a model. Continuous time model, great. It's the dynamics of the system. And that's an ODE model. And that's maybe what you're familiar with, okay? You could integrate it or play around with it as you see fit. But we're not going to do that. We're going to look at what's called the actor model of this system here. So what we're going to do is we're going to firstly break this down into a block sort of style diagram. And if you haven't done control before, you'll see this soon, I'm sure. The idea is you have what's called a plant, which is the system that you are wanting to control, in this case the helicopter. And that tells you that it has some sort of state to it. What state is it in? Okay, so state is this sort of quantity that tells you what that system is doing at a particular time. It's the best way of saying it. And the whole goal of designing systems are you design a controller that can see the state of the plant. It's a very old-fashioned term, plant. It's like from 1950s or 1960s when you're modelling old-fashioned electromechanical machinery. And the controller basically gives a control input. It tries to control the plant based on what it sees, what's observable of the state of the plant. Okay? Now, the actor models of these things we're going to see very shortly, but it's the same. It's a very similar concept. We're going to, instead of having DEs floating around and having to write integral equations, we're going to replace this integral equation with operations similar to this, boxes that do things, okay? Which will be, as I said, very useful when we look at state machines and hybrid systems where there's continuous time and discrete time stuff going on at once, and it starts getting very messy. Okay, so what's an actor model of a system? What I want you to do is I want you to think, if you've used Simulink before, probably most of you done engineering mechanics, I think you still use Simulink in that. Simulink is essentially like an actor model of things. An actor model is not driven by writing down integral equations and ODEs and solving them mathematically. It's a computational way of representing a system driven by simulation, which is what we do everywhere now. Okay? So this is old school. If you do that in control, that's old school. You're now, in this subject anyway, going to represent things by what's called an actor model. So a black box, if you like, that has an input and an output and some parameters associated with it. Now, the best thing about the actor model is that we'll have blocks that have specific functions that are universal to many different types of systems. And here's just our basic mappings and everything like that, right? So the system function maps something from X, something in big X to something in big Y, X to Y. Okay. How's this useful? This is how you would represent the helicopter system as an actor model. The idea is that this is the plant, the thing you want to control, the helicopter itself. The input is going to be the torque, and the output is the angular velocity about the y-axis, okay? We don't want that thing to be spinning around, okay? The parameters of the model are shown in the box. So this, remember, this is the equation from before, okay? It's copied down here. So the helicopter has two parameters that are important, right? The moment of inertia thing here and the initial angular velocity. And then whatever it does is it converts a torque to an angular velocity. It's a black box representation of the helicopter. So that's it. These are continuous time functions. This is a real world, you know, these are real world things that are happening. An angular velocity is real and a torque is a real thing. And the idea behind this is, where it really gets its power is, we can go inside this model, zoom down into it, and it's actually composed of two sub-models, which are themselves actors, okay? Here's the helicopter. Now, we can represent the internal model of this as a scaling actor and an integration actor with an initial condition I. Okay, so that's what the little initial condition I is, because integral is always an initial condition. So in other words, all this complex model is it's a concatenation of two actor models. One that just scales something, so y is just a times x, and then this one here where y prime is the integral of x prime plus an initial condition. Okay? The initial condition is one of the parameters, and the scaling is the inverse of one of the parameters. Now, why is this so powerful? Because instead of trying to write out some differential equation somewhere, how do you write that in? You can sort of write an integral equation, write it out in MATLAB in a real clunky way, or you can jump into a nice piece of software like Simulink and drop in blocks that do this for you. They are actor models, a scaling actor model and an integrator. And this also functionally represents what's going on. And for a systems engineer, seeing these two blocks like this tells you a lot more about the system than seeing an equation like that, okay? It's hard to see what's going on here, but I can immediately tell what the parameters of the system are and the ordering and such, which might become important later on. Okay, this is a scalar one. This takes a torque in the helicopter and spits out the angular velocity about the y-axis. You can have actor models with multiple inputs, no worries. So this one here has two inputs, x1 and x2, and one output. So this is its mapping here. It's mapping two things into one. And examples are a summation actor, right? It takes two things and adds them over all t. And also the subtraction. So you're just subtracting the two. So these are just both examples of a black box, two input, one output actor model. Okay, so how does this help? This helps in the design of systems to control our little continuous dynamic system. Now, I'm not going to get into the whole thing of, control. That's a subject in itself. It's massive. But one way of controlling the helicopter is to generate what's called an error signal. Okay, so the idea is this is what we want to control. Well, the angular velocity is what we're interested in. So we're going to set the desired angular velocity. Maybe we actually want it to rotate a little bit, right, at some sort of fixed velocity. That's okay. the actual angular velocity is subtracted with the little actor model here, right? And that generates E, which is called the error signal. How far from some pre-programmed signal are we really? Okay, so it's just the difference. Pretty simple. And the simplest form of control is called a proportional controller. It essentially is just a scalar, okay? A scale, look, that's just the actor model, like an actor model here, right? It's a scale actor model. And it takes the error signal and it basically generates a torque that is just proportional to the error. So Ty is just Ke. It's a very simple type of controller, okay? You can think about it as as the error gets more, right, it's like the control effect is having more effect on the system as well, according to the proportionality here. Okay, big deal. So that's the little closed loop feedback system. It hopefully provides stability. And if you crank in the controller and put the loop in and everything, you end up with a really ugly differential equation, well, integral equation, sorry, to solve. Okay? We have on one side the angular velocity in the y direction, and we have buried inside an integral the same thing. So solving for this is very difficult. You've almost got to, as they do in textbooks, try a solution, find that it works, hey, and then that must be a solution. But you've got to know which one to try in the first place. I've always hated those things. Okay, so here's the actor model of the controller. Once again, you could go and drop this in Simulink in MATLAB in like, a few blocks. The helicopter, you zoom in, it's composed of two elements, the proportional one and the integrator, and you've got a controller on the outer level, which is a proportional one, and then a summation where you're subtracting something. Okay, so for instance, let's say you want the desired angular velocity to be 0. So you set that into the left-hand side of this system because you don't want the thing rotating, okay? We want to set it to be equal to 0. And if you do that, well, things collapse in the integral and all that sort of stuff, and the differential equation comes out like this, which looks simpler, but it's still messy because you still have the angular velocity in an integral and it's still on the left side as well. Ugh. So if you solve that, I don't care how you solve it, but if you solve it, it comes out as a little equation like this. What is that equation? Well, it's just a little decaying exponential with some constant values in here times a step function, so it's t greater than 0, and with an initial condition here. So in other words, if k is positive, so that this term is still negative overall, then this decays away over time, and eventually this thing here will decay to 0. Okay? Given an initial value and some decaying exponential, this thing will, over time, disappear. Okay, so it will go to 0 over if and only if k is greater than 0. Now, how does this help us? It helps us formulating our models, and we're sticking with continuous time now because that's what we're familiar with, because if you wanted to start tweaking this thing here, it's very easy to do in this sort of graphical loop here by, clicking on this and chucking in a different value for k, right? And a simulator will then go and do all the integration for you and happily reproduce what the output's going to be, okay? And more often than not, this is how you interact with control systems these days. Maybe in the 1960s, you might want to have solved integral equations like this and gone and looked them up in books and, manuals of how to solve integrals of different forms. But these days, you are formulating things in actor models. And all you're doing is chucking it into a simulator, basically, and then adjusting things as you see fit. Isn't that great? Software does everything for us. It can get us fine-tuning controllers and all that sort of stuff. Brilliant. Not so. And this is going to lead into the next 3 to 4 lectures. Can the controller behave differently when you go and implement it in some sort of software case? What if these signals here, so this control, where is this really implemented? Is it some K somewhere on a circuit or something? No, not really. If this controller is complicated, this is programmed in software, instruction after instruction after instruction, fixed times between the instructions. Oh, interrupt. Whoa, what the heck happens? When that controller is implemented in software, all bets may be off, especially if there are interrupts. Can you imagine a controller keeping a helicopter from spinning around, but it's now getting interrupts, right, which are then going and running code, which may mean that the act that it's supposed to be doing of performing control might be delayed or something like that, or might not be done at all. More issues. Angular velocity in practice. Angular velocity is being fed into this actor model here, right, to be subtracted. But if this is a computer system here, right, doing sampling and then multiplying and stuff like that, well, a computer multiplies things. You need a computer to do that. Then this is no longer continuous, is it? It's sampled, and in particular, how's it represented? Bits. Even worse, it could be right, an affine model, which you have to worry about, right? The real value of the sensor versus what's reported. Might be a 16-bit number or something like that. Oof. How do you incorporate noise as well? Okay, if it's a digital value now, what does noise really mean? Wow, it's starting to get really complex. And lastly, what happens if a sensor goes down, okay, or an actuator? Even worse, what happens if the software goes down? There's no fault tolerance here. If there's software that's implementing this control and multiplying the numbers, right, that's all it's doing, and that goes down, well, what's going to happen? You open loop again, right? This loop breaks and your chopper's going to spin around. You've got no control action again, okay? So these are very important things to consider. And if you've done control systems, you probably haven't even thought about it. That's in software. Software is a cyber system. It's sequential. Timing is very important with this, and it operates on discrete, sampled versions of the data. Okay? So I'm going to leave it there, and I want you to think about how we can address some of these issues for next week. All right, and I will scan in this book and put it online for you, some of it.